Hello, and welcome back to Math 3322. I am Dr. Amanda Keith, and today we're going to be talking about section 2 of chapter 7, or section 7.2 of our course. So, reminder, chapter 7 is all about decimals, percents, and real numbers. Specifically, chapter 7.2 is about operations on decimals. So you should be able to use models, drawings, strategies to develop algorithms for decimal operations and use scientific notation for decimals and strategies for mental computations with decimals and estimations. So adding decimals, we learned last time that we can represent decimal values using base 10 blocks. And so if we take the numbers 2 and 1600ths, or 2 and 1/10 1600ths, we can represent it using base 10 blocks with 2 100 blocks, 1 bar, and 6 small blocks. This is where we have the small block representing a 100th. So you would need a little key here. Small block is 1/100th, or that. And same thing, we can represent 1 and 7/10 300ths using 1 large block, 10 bars, or sorry, 7 bars, each representing 1/10, and 3 100ths. We can group these together to add them. So we have 6 100ths and 3 100ths. That gives us a total of 9 hundredths. 1/10 plus 7 tenths is 8 tenths, and 2 ones plus 1 1 is 3 ones, which gives us 3 ones, 8 tenths, and 9 100ths, or 3.89. We can also change the problem to one that we already know how to solve, so one that's involving fractions. So we could break down, instead of representing using base 10 blocks, we can represent using these fractional representations, expanded form of the decimal values. And then we sum together the component parts. You probably have heard the phrase add to or combine the like terms. So the like terms here are our ones, our tenths, and our 100th. All right, so as we move into multiplication and division, I wanted to remind everyone how we typically use an algorithm to multiply or divide multi-digit integer numbers. So in Math 3321, if you've taken it before, or if you are taking it now, or you'll take it in the future, we will go over how we develop these algorithms for multiplication and division with integer numbers. In this course, we're mainly just going to be using those algorithms. But I wanted to remind you how we do that. So if we take values like 27 and 45 and we want to multiply them together, the typical way that you would see this done using our standard algorithm in America is to stack the numbers 27 and 45 on top of each other. And then we multiply by saying, okay, 5 times 7 is 35. So I put the 5 ones of 35 here, and I have 3 tens from 35. So I'm going to put the 3 here to remind myself that I have 3 tens that I still need to think about when I'm multiplying these numbers together. And then I'm doing 5 times 2. Now that 2 represents 2 tens. So when I do 5 times 2, that is 5 times 2 tens, or 10 tens, which is actually the same thing as 100. And then I had 3 tens left over from 35. So I have 13 tens from multiplying 2 tens and 5, and then adding my 3 tens left over. So I have 1 and a 3 here, and 1 100, 3 tens. Now, you probably don't hear people explaining it this way at length, but I want you to remember where we're getting this algorithm. So you would probably just hear someone say, okay, 5 times 7 is 35. Write the 3 up here, write the 5 down here. Then 5 times 2 is 10, plus 3 is 13, write 13 here. Then we use a 0 as a placeholder because now I'm going to be looking at the 4 of 35. Now that 4 represents 4 tenths. So every time I multiply the 4, I'm really multiplying by 40 or 4 tenths. So that's why we have a 0 there as a placeholder, is because I'm already working in the tens place. So 4 times 2, or 4 times 7, or 4 tens times 7 is 28 tens. So I'm going to have 8 tens and 20 more tens. So 4 times 7 is 28. So I put my 2 at the top and my 8 at the bottom. 4 times 2 is 8. 8 plus 2 is 10. So I write 2 a 10 here. And then I sum these values together. 5, 3 plus 8 is 11. So I've got 1 carries down and 2 here. 1,215. Now, this is one algorithm we can use to multiply multi-digit numbers. I really like the partial products method because I think it illuminates what's actually happening in the multiplication a little bit better. So what partial products does is it takes the numbers 27 and 45 and it breaks them into the tens and the ones place. So 27 is just the same thing as 20, 2 tens and 7 ones, or 20 and 7. And 45 is the same thing as 40 and 5. That should be a addition. And then I can use the distributive property to multiply these out. So I know I'll have 20 times 40, and that is 800. I'll also have 20 times 5, that's 100. So what I've done here is I've distributed 20 to 40 and 20 to 5. And then I need to distribute my 7. So I'm going to say 7 times 40 is 280. And 7 times 5 is 35. Then I can sum together all of these values. So I've got 5 ones, 8 plus 3 is 11. So then 8 plus 2 is 10, plus 2 is 12. So I got the same number that I got when I did the standard algorithm. So either of these ways are ways that we can multiply multi-digit numbers by hand. All right, so moving on to division. We have a standard algorithm for division as well, in which we kind of make a division box where we have 1,583 divided by 25. Now 25 is the divisor, and 1,583 is our dividend, and we're looking for the quotient. So the quotient is the answer of a division problem. So what we typically do when we use long division is we look at each place value of our dividend and we ask ourselves, how many times can the divisor go into that number? So when I look at 1,583, I look at 1 and I say, how many times can 25 go into 1? It can't. How many times can 25 go into 15? It can't. How many times can 25 go into 158? Now that, I know that there are multiple 25s that I can get out of 158. So I know 4 times 25 is 100, 6 times 25 is 150. So I can think that 25 can go into 158 6 times. And then I multiply 6 times 25, I know that's 150. Now I subtract and I see what's left over. I'm gonna have 8 left over, and then I bring down the 3. And now I ask myself, how many times will 25 go into 83? Well, I know 2 times 25 is 50, 3 times 25 is 75, so it will only go in 3 times. So 3 times 25 is 75, and then again, I subtract 83 minus 75 is 13 minus 5 is 8. Now I don't have anything left to bring down. In some cases, we might say the answer here is 63, remainder 8. Or we could find a decimal value of this number, which is going to be pertinent to today's lesson. So what I'll need to do now is I'll need to add our decimal place. Now, 1,583 didn't have a decimal, but we can always add 0.0 and it means the same thing. And I'll have also a decimal on my quotient. And so I can bring down a 0 and I'll ask, okay, well, how many times does 25 go into 80? Again, it's going to go in 3 times because 3 times 25 is 75. 80 minus 75 is 5. I'm running out of room. 80 minus 75 is 5. And then I will have to add a hundredths, 0 hundredths to my algorithm as well. So I'll pull that down. And then I say, okay, how many times does 25 go into 50? It goes in twice. And 2 times 25 is 50. And I have 0 remaining. And so this is the terminating decimal that we will get from this answer. And you can do this in your calculator as well, but it's important to know how to do it by hand if you're going to be teaching these grades. Okay, so now that we've reviewed that, we can go into talking about multiplying decimals. So there is a typical rule of thumb that if there are n digits to the right of the decimal point in one number and n digits to the right of a decimal point in the second number, we can, when we multiply the two numbers, ignoring the decimals, and then place the decimal so that there are m plus n digits to the right of the decimal point. So I want to do one example by hand, and then we can go into using this strategy. But if we look at 1 4/10 300ths times 6 2/10, I can use that partial products method to multiply this out. So what this would mean is I split my numbers into 1 plus 4/10 plus 300ths. And I'm multiplying that by 6 ones and 2/10. And now I can distribute across these and find all of the partial products and sum them together. So 1 times 6 ones is 6 ones. Then 4/10, oh, let's go the other way. Let's do 1 times 2/10. 1 times 2/10 is going to be 2/10. And now 4/10 times 6 ones is 24. And then 1/10 times 1 is just 1/10. 4/10 times 2/10 So remembering the properties of multiplication, commutative property, which means that we can change the order, and associative property, which means it doesn't matter which we multiply together first. So I think about this as 4 times 2 is 8 times 1/10 times 1/10, which is 100th. So I have 8 times 100th, or 800ths. And then finally, I have to distribute this 3 100ths times 6 ones, which is 18 100ths. And then 3 100ths times 2 tenths. That's going to give me 6 1,000ths. All right, and then I can combine my like terms together. So I only have 1 1, so I'm going to have 6 ones. And then I have tenths. I have 2 tenths and 24 tenths. 2 tenths here, 24 tenths here. So that's 26 tenths. Which is actually the same thing as 2 ones and 6 tenths. All right, and then hundredths, I have 8 100ths and 18 100ths. So that is 26 100ths. And then I have my 6 thousandths. And 26 100ths is the same thing as 2 tenths and 6 100ths. So again, I can combine my like terms and say, all right, well, I have 6 ones and 2 ones, so that's 8 ones. Then I have tenths. I have 6 tenths and 2 tenths, that's 8 tenths. Then hundredths, I have 6 100ths. And thousandths, I have 6 1,000ths. So 8.866 should be our answer. All right, so we can use that standard algorithm as well, using the fact that if we have n digits in one decimal and m digits in another decimal, then the number together should have m plus n decimal points, decimal places. So here we would take 6.2 times 143, 1.43. We can use that standard algorithm. So 3 times 2 is 6, 3 times 6 is 18. Placeholder, 4 times 2 is 8, 4 times 6 is 24. Then we have 2 placeholders, 1 times 2 is 2, 1 times 6 is 6. Sum these together, 6, 8 plus 8 is 16. 1 plus 1 is 2, plus 2 is 4, plus 4 is 8. 6 plus 2 is 8. And then because this value, 6.2, has 1 decimal and 1.43 had 2 decimals, I know this number should have 3 decimal points, 8.866, which is the same value we got when I did it by hand using partial products. All right, and so we could do the same thing with 0.02 and 0.013. So we use the standard algorithm to multiply this out. 2 times 3 is 6, 2 times 1 is 2. And then because 0.02 had 2 decimal values, and 0.013 had 3, we're gonna have 5 total. So we can move our decimal point over. And then we're gonna have situations where we're multiplying just by multiples of 10. So 1000 times 3.6, I like to think about when we're multiplying by multiples of 10, 1000 is 10 cubed. And so this just means I'm going to have 3.6 1000s or 3600. And we could use the standard algorithm here as well, where we do 36 times 1000 and then one decimal place, but coming from that 3.6. Then we have scientific notation. This notation is used in science a lot to handle large or very, very small numbers. So we talk about a light year is this very big number of miles. And we can express it using scientific notation by having our value times the number of decimal points we want to move it over. So the idea of scientific notation is that we want to place a decimal point where there's one significant figure to the left of the decimal point. So significant figures are values that are non-zero. So I want one of those to the left of my decimal point. And so to get a decimal point between this 5 and this 8, I need to move my decimal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 spots over. So I'm going to multiply by 10 to the 12. We can go the other way as well and have a really, really tiny number. The mass of an electron is this very small number of atomic mass units. And here I want to put my decimal point again between that 5 and 4. So I need to move my decimal to the right 1, 2, 3, 4 places. So this negative exponent is going to move my decimal to the right. So I have 4.5 or 5.4875 times 10 to the negative 4th power. So like I said, it's a positive number written as the product of a number greater than or equal to 1 and less than 10, so 1 digit, and an integer power of 10. To write a negative number in scientific notation, we treat it as a positive number and join the negative sign in front of it. So here are some examples. If we take 413,682,000, we want to put that decimal point here. And so that means I'm going to have to move 1, 2, 3, 4, 5, 6, 7, 8. So I'll have 4.13682 times 10 to the 8th power. And here I need to put my decimal point between the 2 and the 3. 1, 2, 3, 4, 5 decimal spots over. So I'm going to have 2.31 times 10 to the negative 5th. This one I just need to move over once, so that's going to be 8.37 times 10 to the 1. And as mentioned previously, we can have, we want our decimal here, so this is just going to be negative 1 times 10 to the 7th because I'm moving my decimal 7 spots. We can go the other way as well. So 6.84 times 10 to the negative 5 means that this decimal point 684 has been moved 1, 2, 3, 4, 5 places. Wait, I messed up. What did I do wrong? I went to the right where my decimal needs to go to the left because I have negative exponent. So this number is actually really, really small. I have to go 1, 2, 3, 4, 5. I'm going to have 4 zeros and then 684 on my decimal. There we go. Now I get to go to the right with 3.12 times 10 to the positive 7th. So 312. There should be 5 zeros because I've moved my decimal to the right. We can always add our commas to help it be a more easily read number. So 31,200,000. And then we have negative 4.08 times 10 to the fourth. So 4.08 times 10 to the fourth. I'm going to have my decimal moved over 4 spots, and it's a negative number. So negative 40,800. All right, so we can divide decimals as well. So when our divisor is a non-decimal, so this 4 here is a non-decimal, we can use that same standard algorithm, or we can think about breaking down our value. So we can think about making 128.6 into a fraction, and then when we divide by 4, we're really just going to divide 1,000 or 12,860 by 4, and that's the number of 100ths we'll have. Or we can use that standard algorithm, as I just mentioned. So we would ask ourselves, how many times does 4 go into 12? 3 times. So 3 times 4 is 12. Then 12 minus 12 is 0. So I brought down my 8. How many times does 4 go into 8? 2 times. So 2 times 4 is 8. 8 minus 8 is 0. Bring down the 6. How many times does 4 go into 6? 1 time. So remember, I just had to place my decimal above directly the number when I'm doing long division this way. So 4 times 1 is 4. 6 minus 4 is 2. So I need to keep going to find my terminating decimal. Bring the 0 down. How many times does 4 go into 20? 5 times. So 5 times 4 is 20, and then I get a remainder of 0 here. So we can use long division the same way pretty easily if we have a divisor that is a whole number. But if the divisor is not a whole number, then we can actually make it into a whole number by just multiplying by both values by the same amount. So 1.2032 divided by 0.32. We could think about this as 1.2032 divided by 0.32. Thinking of this as a fraction. And when we multiply the numerator and the denominator both by 100, it maintains the value of that because I'm really just multiplying by 1, because 100 divided by 100 is just 1. So I can make this into an equivalent problem, 1 to 0.32 divided by 32. So these two problems should give you the same answer. And so when we do this, we multiply the divisor and the dividend both by 100 and move the decimal point to the right, and then compute our long division. So saying, all right, 120, how many times does 32 go into 120, and etc. So for a lot of these problems, you are just going to be able to put something into your calculator. But it's really valuable to be able to do a lot of these computations mentally and to develop these number sense skills. So one strategy we have for mental computations with decimals is called breaking and bridging. So this is where we're going to split the numbers apart into numbers that are friendlier for us to add together. So I might say, all right, well, I can combine 1.5 and 3 together to get 4.5 or 4.5. And that's easier for me to do first. And then I can add the 0.7 on after. So then I get 5.2. And then adding the 4 onto that, I get 9.2 plus 0.048, and then I'm able to add on those decimals. A way that I might think about doing this problem is to break up 3.7 into 3.5 plus 0.2. And then I can add 1.5 and 3.5, and that's going to be 5 total. Because 1 and 3 gives us 4, and then the 0.5 and 0.5 gives us another 1. So then I have 0.2 plus 4.48. And then I might combine the 4 and the 5 to get 9 plus, and then 2/10 and 4/10 is 6/10, 8/100, 9.68. There we go. Which is the same value that we got splitting it the other way. Then using compatible numbers, so finding numbers that would make a whole number sum together, just kind of like I did splitting up 3.7 so that I had a compatible number. So here I can pretty easily identify that when I have 91/100ths and 9/100ths, that's going to sum together to a whole number for me. And I also have 85/100ths and 15/100ths. That's going to make a whole 1 for me as well. So putting those together, what I would think in my mind is when I put the 9/100ths here, that makes this number into 8 and this number into 4. 8 plus 4 is 12. And again, if I move my 15/100ths first, then I have 4 and 0. And then I have 12 plus 4 is 16. And then we could make these into compatible numbers. So I say, all right, well, I can think about taking 2 of these hundredths, getting rid of them, and taking 4 of these hundredths and getting rid of them so that I have 2 numbers that are compatible and will make a whole number easily. So 25 and 75/100ths together gives us 1, and then 1, 9, and 3 will give us 13, and then 6/100ths there on the right. And then balancing with decimals and subtraction. So 4.63 is, I can add 0.3 basically to both of these numbers. So essentially what you might think of in this case is when I'm subtracting 4.63 or 1.97 from 4.63, I'm finding the distance between those two numbers on a number line. And if I move both of those numbers up 0.3 on the number line, the distance is still the same. So if I shift both of these numbers up 0.3, and that will make 1.97 move up to 2, it's going to be a lot easier for me to subtract 2 instead of 1.97. This is actually something that you can use all the time. So if I wanted to subtract, I don't know, 87 from 1,000, you might, using our standard algorithm, be like, oh, I'm going to have to do a lot of borrowing, a lot of carrying. Say, all right, well, I need to borrow from 0, but I don't have a 0. I need to borrow from 0, so 10, so 9, 9, 9, and then you have to subtract this way. That's pretty complicated. But instead I could just subtract 1 from both of these numbers, shift them both down 1, and this is going to be the same thing as 999 minus 86. And then the numbers are a lot easier to subtract. 913. So using mental math is going to be an important part of building number sense with children of these elementary grades. Again, we can make decimal division into other problems by, again, multiplying by some value that's going to make our problem into a division with whole numbers. So in this case, we had 0.25 as our divisor, 8 as our dividend. So this is like 8 divided by 0.25. And if I multiply by 4 on both, then this is the same thing as 32 divided by 1, which is 32. Then we can do rounding. I'm not going to spend a lot of time here, but just practicing with what our decimal places mean. So if I want to round to the nearest hundredth, so hundredths place here is 5. So if I'm rounding, I have 6 thousandths here. So 6 thousandths is closer to 100th than it is to 0 hundredths. So this will be 7.46. So I round up. And then to the nearest tenth, again, 5 will round us up. So I'm going to have 7.5. Nearest unit means our ones value. 4 rounds down. So 7. The nearest thousand, here our thousand is 7. So we're going to round down to 7,000. To the nearest 10, we'll round up to 750. And to the nearest 10 here, we'll round down to 70. Then we can round numbers to estimate answers to computations. When we have to be careful though, because when we round numbers and then perform computations with them, the results may be pretty different from the actual answer. So estimation strategies like front-end clustering, grouping to nice numbers, these were investigated to with whole numbers to work also with decimals. And round off errors, we get compounded errors when we do computations on numbers that we've rounded. So the rule of thumb when it comes to using rounding in science is to report the final result. We shouldn't report them with more significant digits than the number used with the fewest significant digits. So if I'm taking 1.253 times 10 to the 7th times 1.4 times 10 to the 3rd. This number has the fewest number of significant digits. It's only 2. So when I multiply these things together, this will give me, I don't know, some value, 1.253 times 1.4 is 1.7542 times 10 to the 7th times 10 to the 3 is 10 to the 10th power. Now I shouldn't report my answer like this because I have too many significant digits. I should only report up to 2 significant digits if these numbers have been approximated. So I would just report 1.7 times 10 to the 10th approximately. And non-zero digits are always significant. Zeros before other digits are non-significant. Zeros between non-zero digits are significant, and zeros to the right are significant. Let me erase this. To avoid uncertainty, zeros at the end of a number are significant only if they're to the right of a decimal point. So like 1.5208 would have 5 significant digits. This 0 is not significant, but this 0 is significant because it's between non-zero digits. All right, and that's section 7.2. So let me know if you have any questions. I will be at my office hours, and um, available via email as always. So good luck, and I will see you soon.